Okay, let's go ahead and get started. Hello, everyone. My name is Tara Van Cleve, and I am a marketing event manager for the developer initiative here at Oracle. Thank you for joining us today for our workshop on graph analytics for beginners. We're excited to show you step-by-step how to integrate multiple data sets, use a graph, and facilitate additional analytics that can lead to new and potentially groundbreaking insights. After the lab walkthrough, you'll have the opportunity to apply what you've learned on your own in your free tier environment. If you have any questions during the workshop, please ask them in the Q&A area, and we'll have solution experts available to answer them throughout the session. This workshop is being recorded, and the recording link will be available on the event page and also sent to you via email shortly after the event concludes. You will also have the opportunity to participate in a short quiz on the material covered in today's workshop. Upon completing the quiz, you'll receive a Developer Masterclass badge that you can share to your social media, recognizing your commitment and earned expertise. Today's workshop will be presented by Hans Fieman, Product Manager of Spatial and Graph, and Jayant Sharma, Senior Director of Spatial and Graph Product Management. So without further ado, I will turn it over to Hans.
Okay, thank you. Thanks, Tara, and hello also from my side. Thanks for joining us for this webcast today. What we've planned for the session is a more technical deep dive into our graph technologies. What we'll be using is a demo scenario which Jayant will walk you through in a live environment, so that at the end of the presentation, you should have a decent understanding of how to create a graph from relational tables, how to perform pattern matching queries on the graph, how to execute graph algorithms using the Oracle Graph technologies. So all the things which are required to really get going on graph analytics. Throughout the demo part, what we'll be using is our new Graph Studio in Autonomous Database, so that after the session you can go and sign up for the Oracle free tier account, which Tara was just mentioning, using the link you have on that slide here. And what you want to get with this is the promotional offer, which gives you access not only to the cloud infrastructure with its always free offering, but you also get an additional $500 worth of cloud credits. Right? Tara was talking about the App Dev Masterclass series and the possibility to participate in the quiz after the session to earn your badge. So we'll come back to that again later. Right, I don't know if you joined us 4 weeks ago. 4 weeks ago, Jane and I, we held an introductory webcast on our graph technologies, in which we talked about graph analysis in general, typical use cases which we're seeing in the market. So in the interest of time, I'll just give you a very short summary. If you're interested in more details, what I suggest is you check out the recording on youtube.com/oracledevs. Tara might have the URL in the chat ready for you, so you can go and have a look at that session for more background. Here, I really just want to reduce it to one single slide. So what are graphs all about? Well, graphs, rather than using tabular structures to store and manage data, are using a storage model in which entities are represented as vertices in a network, and relationships are represented as edges between these vertices. Like in this little social network on the slide here, right? I have vertices of type person, and like, come on, where are we? Like this guy. And edges of type connection, and the vertices of type person can have properties like name equal to Hugo here. And one interesting aspect of graph databases is that they don't have a fixed schema. So in my social network example here, I can add a vertex of type company, or I can add your edge of type works for, and that will not break my existing applications or analysis, right? The main reason for the popularity of graph databases is that you can perform analytics which are very hard to do on other kinds of databases. So by means of graph algorithms, you can, for instance, automatically determine communities, like the community here. You can find parts which are more important, right? Identify important vertices like the one in the middle, which is the only connection between two communities, for example. And technically, what makes a graph database different from the conventional relational databases or a converged database such as the Oracle database makes it different from a conventional purely relational database is that they treat the relationships, so the edges between vertices, as first-class objects in the database, meaning these edges are explicitly stored, and that is what enables fast traversal of these edges and makes it possible to perform, for example, path queries between these connections very quickly, right? In the context of reachability analysis, or if you want to figure out the shortest path between two given vertices in such a network structure, right? So that's sort of the one slide summary of graph technologies in general. What does that have to do with Oracle? Well, actually, we've been offering graph technologies for many years now with the user-managed product for graph analytics, which we're focusing on today, on the market since 2016. And that product is actually a feature of the Oracle database. In fact, it's one of the multi-model capabilities of our converged database engine. You'll hopefully all know that the graph features of the Oracle database do not require a separate license any longer, but are available without additional charge with every edition of the Oracle database and all relevant cloud services. So that if you have an Oracle database anyway, there's actually no reason not to use it for graph analytics, or to at least try it out. To use the graph features, in the past you could either install the graph server and client on premises, or use it on the Oracle Cloud by installing the OCI Marketplace image, which we're offering. Right? With that, you could then create your graph model from relational data you had, you perform graph analysis, you use the tools in the graph server and client kit, such as the Python client or the visualization tool, the Zeppelin-based notebook, and all the other things to work with the graph. What you would do, if I say, you work with the graph, what you would do is basically two things. On the one hand, you would do query processing, where from one or more given starting points, you investigate the surrounding connections of a given vertex by, for example, searching for specific patterns. So maybe if we take the example of the Panama Papers, right, where you investigate a specific person, you start with this person, you find out he owns a bank account which is used to transfer money to a corporate bank account which belongs to a company on the board of directors of which is the wife of the first person. So for every vertex, the person, the account, the company, and so on, you determine what it is related to, and you end up with a path. In this case, a circular path. Right? That's the one class of analysis you can do. The other thing you can do with graphs is to run graph algorithms from graph theory, for example, to find bank accounts which are particularly central in the graph, which can then serve as a starting point for your analysis. Now, to make it very easy for you to get started, what we've developed and what we've launched earlier this year is what we call Graph Studio in Autonomous Database, which is a complete graph database and analytics environment, which is a feature of the Autonomous Database. That doesn't only mean it uses the Autonomous Database as the persistence layer, but it is actually an integrated environment which we are managing for you. So it inherits all the self-driving, self-securing, self-repairing capabilities of the Oracle database. And it includes a modeling tool that helps you to turn relational tables into a graph. It includes a notebook-based environment, so you can work with the graph and share the results. And it comes with graph visualization also included. And of course, it sits on top of the graph analytics engine, which we've had out on the market for a number of years. Now, so what is it that we want to show you today? What we've prepared is a little demo scenario that starts in the relational world, in this case in a fictitious financial services environment, where we have two tables, one containing information about bank accounts, like account number, account holder, and so on. The other storing the transactions between these accounts, so essentially the two account numbers and the amount of money which is being moved between these accounts. The first thing we'll do with these tables is to convert them into a graph model. Right? I'll explain how this works in general, and Jayan will show this in practice. And once we're done, then what we'll try to do is to find circular payments, like this little sketch, this little graph here at the bottom right, where money is moving from account 2 to 833 to 672 to 910 to 274, and then back to 2 again. And again, I'll explain how that pattern matching works in general. I'll give you a bit of an introduction to PGGL, the property graph query language, and Jayan will demo this using this little example. And finally, we'll show you how to execute graph algorithms. So, for example, in order to identify which accounts are particularly important, right, which can act as a starting point for your analysis. Right? I'll talk about what algorithms we have and how to use them. And again, Jayan will show you what it takes to compute, in this case, the PageRank value for the bank accounts. Right? So that's the plan for today. The tasks are the following, right? In summary, first, we'll create a graph from relational tables. Then we'll move the data into the appropriate data structures. Then we'll perform graph pattern matching queries. And finally, we'll execute graph algorithms, as in this case, PageRank. What we'll be using is Graph Studio and Autonomous Database. You could potentially also use the Graph Server and Client Kit, so our user-managed offering. But in that environment, you wouldn't have all the automation which we provide with Graph Studio, and you would also not have the UI to model your relational data as a graph, but you would need to manually create the create property graphs DEL statement. What that means, I'll come to in a moment. This entire demo scenario is documented in a Live Labs workshop. I don't know if you've been looking into the Live Labs in the past, but these Live Labs workshops, they come with detailed step-by-step instructions so that after today's session, you can easily try this out yourself. Right? The direct link to the workshop, which we're using as a basis for our session today, is displayed here. This is actually one of several workshops covering graphs, not to mention the huge number of workshops on all kinds of other Oracle technologies. In the interest of time, and because there's really nothing graph specific in that part, we will not walk you through the creation of your cloud account in today's session. Right? Most of you will probably have one anyway, I guess. The second prerequisite, enabling Graph Studio, is actually pretty simple. Right? All you need to do is to create a database user and give it the appropriate privileges, for example, in the OCI database actions functioning in OCI. That step is also well described, so we'll skip it here. And finally, also loading the sample data is probably something we've done before. So again, it's not particularly graph specific either, so we won't cover that here as well. Right, so that gives you a little bit of background, and I would say, without further ado, let's focus on the things which are really specific to graphs. And the first thing which I'd like to cover is how to convert relational tables to a graph. Right? What we'll use for this example is actually not the bank accounts and bank transactions schema, but we'll use the sales history schema, which you may already be familiar with. Jay in his demo will show the bank accounts and bank transactions, but I'd rather start with sales history because it's a little more comprehensive and therefore a little more educational. And so what you can see on the left-hand side is an entity relationship diagram, which I assume many of you will be familiar with if you are coming from a relational background. Right? The trained eye will recognize something which is pretty much a star schema, which usually has one fact table in the middle. In this case, the sales table, which contains all the order lines. And each order line is related to one product, while each product obviously is related to 0 or more order lines, meaning we have a one-to-n relationship here. Right? Same thing with the relation between sales and customers. In the relational world, all of this is very well defined. There's a strict theory behind it. In fact, you need the reason we have the sales table in the middle. We need the sales table in the middle as an intermediate table between customers and products, because you cannot model many-to-many relationships between customers and products otherwise. Now, the graph model is different in this respect, right? It doesn't have this fixed schema. You can connect anything to anything. So this leaves us with the question of how we can convert this relational model to a graph, meaning what's going to become a node, what's going to become an edge, and what are the properties associated with either of them. And there's no single answer, right? The answer actually depends on what you want to do. So let's assume we want to use the data from the sales history schema for a marketing project, where we'd like to predict which products a given customer would likely be interested in on the basis of previous purchases and the purchases of similar customers. That's a typical product recommendation type of scenario. First step would be to figure out, okay, what information do we really need? In this case, we would only require the customer information and the product information, and we could connect the two by looking at which customer has purchased which product. Right? Unlike in the relational world, they can have one customer being associated with many products, while at the same time having the product being associated with many customers. This many-to-many relationship doesn't cause an issue in the graph world. And in fact, that is what makes graphs interesting from an analytics perspective, because you can now easily determine products which are indirectly connected to a given customer, which is an information which is not usually taken into account in relational analysis. So once we know what we need, we can go back to the entity relationship model. Right? In this case, we would want to have vertices of type customer and vertices of type product. So every row in the customer table will become a vertex, and every row in the products table will become a vertex. And I mean, not every attribute may be relevant, so I pick and choose which attributes I want to take into account as a property on either vertex in my graph. And the rows in the sales table can be modeled as an edge connecting the respective customers and products. Right? Whenever a customer has purchased a given product, there's an edge. And what happens to the attributes in the sales table, which are not foreign keys? Well, they can become properties on the edge, so that an edge between a given customer and a product also holds the information about the quantity and the price and whatever. Now, I can express this mapping in a create property graph statement, like the one on the right-hand side here, right? With this DDL statement, what we're creating is a new graph, in this case called sh_purchase, which maps the customer table with some of the attributes to vertices, which maps the products with some attributes to vertices, and finally, which creates an edge from each row in the sales table, connecting customers and products and associating each edge with, in this case, the quantity underscore sold attribute. Right? That create property graph statement uses a variety of defaults from which it picks up from the Oracle Data Dictionary, such as primary keys, foreign keys, the object names. But you can always overwrite those, like we've done in the case of the edges here, where we've explicitly stated that the label on the edge would be purchased, for example. Right? If you're interested in all the bells and whistles, you can find the full specification of the create property graph statement on pgql-lang.org. Right? That's where we specify. Okay, so now we've got the mapping, and now that we have the mapping, you can go ahead and try out your analysis. But that's not necessarily the end of it. It's actually not at all uncommon to modify the graph model to better suit your analysis. That can mean either small changes such as adding or otherwise modifying properties of vertices or edges. You could also do more fundamental changes like converting edges to vertices. Right? It may be necessary to create a vertex of type sales order, let's say, if you want to link that to the promotions in this data model. This is something which you might need to do because you cannot link something directly to an edge. Or if you want to merge your newly created graph with other data sources, right? As the graph model doesn't have a fixed schema, you're actually very free in what you can add or modify. That said, most of our customers actually come from a relational background, and they essentially all map to the graph, map the graph to tables which they had before, essentially reflecting the relational model in the graph schema. Right? Okay, so let's look at that in practice. And with that, I would like to hand over to Jayan to show us what this process looks like in Graph Studio.
Thank you, Hans. Okay, so as Hans was describing, today we're going to walk through this particular live lab. So the live lab is available. You have the URL, and all the steps that I'm going to walk through are available in this. So when you go to the URL, you can choose launch, one of these versions. And when you do that, it takes you to this step-by-step instructions. What we're going to do is starting from step 3 onwards. Actually, Hans talked about step 4, so I'll do that first and then move back. But we will not be doing the process which says how do you provision a free trial account. You can follow that itself, or we've got a few slides which show you how to do that. And we will also skip the part where we talk about provisioning and a database instance. I will briefly describe what is needed in order to use graphs in that database. Okay, so once you create a database instance, right, you have a database instance. I have one created. When you click on it, it brings you to the detail page for that database. And on the tools page, it gives you access to the tools that you will use in this lab, one of which is the Graph Studio, and the other one is Database Actions. So when you launch Graph Studio, it'll ask you to log in with a user and a password that you create using Database Actions, and I will show that subsequently. The first thing that you do when you log in is you get the landing page, the home page, which tells you if you already have some existing information or data. It'll tell you which graphs, which notebooks, etc. you have. Or if you don't, it shows you what's the first step, which is you need to start modeling. Now, how to navigate this interface? That is the home page. the modeling, which is the first step that you do, is you model your existing data as a graph. Then you actually create a graph. That's the second part, instantiate the graph. And third, you interact with it in an interactive notebook. So the modeling process is, you click on that, it brings you to a page which shows you what data you have. So I have some data, as does Hans. So let's take the bank accounts and the bank transactions. And the reason I can see Hans's data is because he, prior to this, actually granted me access in the database to his data for the purpose of this webinar. So I decide which tables I want to use. I'm going to take the accounts and the transactions, that is the transfers between these accounts, and I want to create a graph from that. And the purpose of that essentially is to look for circular transactions, right? So we want to create these graph, and then we're going to look at cycles, and I'll show you what that is subsequently. So once we have these, we let the modeler inspect the tables, and if they have the foreign keys and the primary keys, as Hans was describing with the sales history schema, the modeler will suggest a model which says, let the accounts be vertices and the transactions are the edges between those vertices. Now, we can accept this, but it is good practice to also inspect exactly what it is going to suggest. And depending on what we see here, I'll explain why. So what this is done, when you inspect it, what it does is generate a DDL, a data definition, and that is a create property graph statement, which essentially says the vertex tables are going to come from the bank accounts. The key to that table is the account ID. These are the properties that the vertices will have. The edges are going to come from the transactions table, and here is the definition of the edges, which in this case, when we inspect it, we realize that we probably have to change. It says that the source is the to account ID, which actually should be the destination. And the destination is the from. And the reason this happens is when you just inspect the database metadata, the constraints may have been ordered in some arbitrary way, maybe by the name of the constraint or by when the constraint was defined, but you don't know that. So you want to come in and actually ensure that this is correct. So one of the things you can do is just modify it here if you want, or you can use the tool. And I actually want to make multiple modifications. So one of the things I want to do is swap that edge, right? Make sure that the source is the from and the destination is the to. That's one modification. I can go back here and verify that that happened. So the source became from, destination became to. The second modification I want to do is, since I keep referring to these as transfers, I just want to call these edges transfers. And I will be referring to the vertices as accounts, and therefore I want to just give them the label as accounts. You can choose to rename the properties if you wish. And if you're satisfied, you can take one look here. So when I added the labels, that has been added. The label has been added. So like I said, I could have just come in here and put all this text in, but rather than worry about typos, it's better to just do it in the tool. So that was the modeling step. The next thing is to create a graph, but I'll hand it back to Hans for now to continue with his presentation.
Yes, thank you, Jayant. Let me go back to the slides. You can see my slides again. So you've seen how we're doing the modeling in Graph Studio. The next step, once we have the create property graph statement is to actually populate the appropriate data structures. And the way this works is let me take one step back. What you need to do in order to be able to run complex graph queries and to perform graph algorithms and so on is the appropriate in-memory data structures. And in order to get there, we move the data from the physical source tables into the appropriate data structures, right? So first, what we do in Graph Studio is we persist the graph in database tables. So we have one table which has all the vertices. We have one table which has all the edges. And the reason why we have them is that they enable you to store the data in a schemaless way, such that you can either use SQL or the property graph query language on these tables to query the data and to modify the data. In the user-managed product, so on premises, or if you use the OCR marketplace image, we're also offering a direct mapping from relational tables to the in-memory data structures. So essentially giving you a schema-bound graph, which can be very useful if you don't require the flexibility of a schema-less model. In that case, you don't need to first move the data into the additional tables and then load the data into the appropriate in-memory data structures. That option, for the time being, is not yet available in Graph Studio, but we're working on it. Right, so that's how you get from the plain relational model using the create property graph statement to the appropriate data structures in memory. Right, now that we have created the graph, we can actually start querying the graph. Right, for that purpose, what we're offering is PGQL, the property graph query language. At the moment, there is actually no standard graph query language or API yet. There's a couple of initiatives, but we are actually, as we speak, we're actively working on the standardization together with the other main players in the industry. And the result will probably look similar to what we have built. What we've done is we've designed PGQL in such a way that it allows you to identify graph patterns. And in order to identify graph patterns, of course, you need to specify the different kinds of patterns, whether it be fixed length patterns or repetitive patterns of variable length. And what we've done is to basically extend the SQL constructs, so select, from, where, group by, order by, and so on, with a match clause for this very purpose, right? The idea is that it should make it very simple for SQL developers to also develop graph queries. Now, if you want to modify the graph, there are insert, update, delete statements, and you've already seen the create property graph statement as a DDL statement. All of these statements, all of the complete language specification is published on, as I mentioned earlier, pgql-lang.org, and it's there together with lots of examples, which is a great reference for anyone working in this space. Right. Okay. And now coming to the actual match clause, the match clause is actually rather intuitive, right? It's a bit like ASCII art. Right? We're using parentheses to represent vertices in the graph pattern and square brackets to represent edges, which are connected to the vertices by pointers indicating the direction, or if you want, explicitly ignoring the direction. Right? The two simple pattern matching queries which we have at the top, either using a directed edge or matching an edge in either directions. Right? We select the variables A, B, and E, where A and B are vertices and E is an edge. Note that we are explicitly specifying a graph in the on statement, because unlike some other graph databases, we can have more than one graph in our database, right? In the statement below those two, what we are also specifying is the label or the type of vertex, and also of the edge, so that we would only retrieve vertices which are those vertices B, right, which are connected by an incoming edge of type transfer to a vertex of type account. Right? So that's the second step. The third one becomes a little more tricky already, in that it is selecting a recursive pattern, right? The slashes here in the match statement with the cleaning star, they indicate that we're looking for patterns with 0 or more edges of type transfer, right? Originating at a vertex of type account, in this case with the account number 4711, right? In a similar way, I can actually also search for 1 or more edges, just using a plus instead of the cleaning star. Or I can specify a fixed number of hops, like a minimum, a maximum, or just a set number. And these variable length paths, they only return the start and end vertices. So if I want to retrieve all the vertices in between, in PGQL 1.3 at least, I need to explicitly specify them, and you'll see Jane doing that in just a moment. Right. With PGQL 1.4, it is actually possible to also easily access the vertices and edges in between and perform aggregations, or also create lists along the selected path. And talking about paths, right? Another key feature in PGQL is to compute shortest paths. Right? You can specify any shortest path if there's maybe 2 or more shortest paths of identical length, right? Any will give you any one. You can specify all shortest paths, or you can also compute the top n shortest paths, as you can see in the examples here, right? In both cases, what you can also see in the statement is that we're aggregating values here. In this case, we're calculating the sum of the amounts on the edge along that path, right? So that would be shortest path, all shortest path, top k shortest path, and so on. If you add a cost function, then you can also compute the cheapest path, meaning the path or paths, it could be more than one, with minimum cost. Right? And finally, there's a couple of built-in vertex or edge functions like in degree or out degree, which return the number of incoming or outgoing edges respectively, for example. Right, so these are the basic language constructs. Here's a couple of additions before I hand over to Jay, and there's another couple of hints here. First of all, you can omit variables if you don't need them, right? Or edge specifiers if you don't need them, like in the top examples here. Then there's the possibility to match more than one label using the vertical R. And finally, you can have a path expression, which you can use very nicely to reduce the complexity of certain queries, right? So if you put all of this together, you'll arrive at a query like the one at the bottom, where we're searching for all the common ancestors of a person with the name Mario and a person with the name Luigi. Right? Here we're using the path specification to represent the edges of type has father or has mother as has parent, and more importantly, we use this in a repetitive pattern for the relationship, right? The plus sign here indicates that we're looking for 1 or more consecutive edges of type has parent in that PGQL statement at the bottom, right? If you try to write this in SQL, this is actually an interesting exercise, by the way, right? You'll notice that due to its recursive nature, it's not trivial. And here in PGPL, it is actually very compact, and therefore it's pretty simple to code and also easy to maintain, right? So that was my little introduction to PGQL, and with that, I'll hand it back to Jayant to show you what this looks like in practice.
So in this lab, if you do the workshop right from scratch, the first step is creating your account. The second step is creating a database. And the third step is creating a user with the right roles and privileges for using graphs. Okay, so let's just quickly do that. If you open up your database, you go to the tools page for that autonomous database instance. You click on database actions. When you created the database, you would have had an admin user. And so you log in as that admin user. What we're going to do now is create a user, who has the right privileges. So in order to do that, you go to the administration, the database users. And Roberta, thanks for answering the question in the chat. So you go here, you click on create user, you give it some name, a password that meets the required criteria. But the most important part is you click on graph enable. And since in this lab, what you're going to do is also use database actions to do things such as loading the data, you also want to give that user web access. So you do these things and you create that user. Once you've created that user, let me log out from this first, because I'm going to use it in a minute. Once you create the user, you click on Open Graph Studio. It brings you here, where you now log in with that newly created graph enabled user. Okay, so while the other thing that we're going to do over here in this is, I said we have to load some data, right? So in this workshop, the other step after you've created the user is to load the data, right? And for that, we will use the database actions once again. So the all used to be called SQL Developer Web. And in that, you're going to use the don't know what happened with the data loading, but I will just use it from here. You click on data loading, and then you can select the file, the CSV file that you want to load, which in my case was, I'm going to have to find it. And then you can go ahead and just follow the steps. You can modify things if you want. You can modify that to be, say, a number, etc. And click finish. So that's the accounts table that got loaded. There were 1,000 rows. Click on data load again and take the transactions table. I could do the same thing, say that the account IDs are numbers, as is the amount. Click next, finish, it will load those. There should be about 5,000 of them, 5,001. And so those have been loaded. Now, these just got loaded from the CSV, so obviously they're missing things such as the foreign key and primary key. So I need to do that. So part of the lab also is a SQL script that does that. So I just copied and pasted the contents of that script here, and that's going to set up the primary keys, etc. for these tables. So it shows me the fact that it's added the primary key constraint, it added something, transaction ID to the transactions, it added the foreign keys to the tables. Okay, so now, so Hans, when I recover from this, so I'm going to shut down and start up again. You want to go ahead with the next steps?
Yes, let me do that. Okay, so before we move on to the PGQL queries, let me briefly expand on the second part of what I wanted to talk about. So not only the graph pattern matching, but also the graph algorithms while you're busy getting things going again. The graph algorithms, for those of you who are not so familiar with graph technologies in general, we have implemented a large number of graph algorithms in our in-memory analytics engine. In fact, it's over 60 of them in the meantime, which allow you to do all kinds of things like ranking, community detection, path finding, link prediction, and so forth. You can see the list of algorithms on the slide here. All these algorithms are parallelized to the degree that they can be parallelized. And if you compare this to other graph databases, you actually find that they scale extremely well. And the output of these algorithms, you can then use either for interactive queries, or you can use them, and that's also becoming increasingly popular. You can also use the output as input to your machine learning platform, right? It could be, Oracle Machine Learning, for example, and the graph aspect, which particularly takes into account the topology of the graph, so the indirect relationships, they can actually improve the accuracy of your predictions quite a bit. Like in the on-premises product, we're actually offering 3 dedicated graph machine learning algorithms, GraphWise and PG2Vec. We are currently working on making them also available in Graph Studio, but again, this functionality is not yet there, but we are on a pretty short release cadence with Graph Studio, so we're continuously adding new functionalities as we go along. Right, so these are the algorithms and the classes of algorithms which you would typically find. What we wanted to show you today is in particular the ranking algorithms. Those ranking algorithms, they're actually used to compute the relative importance of vertices in the graph. And what kind of importance are we talking about? Well, there can be different kinds of importance, right? In some cases, it might actually be sufficient to just look at the number of incoming or outgoing edges, right? Like in the case of how many products depend on a given part, right? Which is just the number of edges connected to a given part, which could be relevant in more sophisticated scenarios, where vertices are particularly important because they are the only connection between two communities. That aspect may be crucial. I think about a graph of project teams, right? If one person is the only person working on two project teams at the same time, he or she may actually be crucial to the success of both projects because of this, right? In other cases, not only the number of connections is relevant, but also how important these connections are, right? So this recursive kind of definition is particularly useful in, let's say, in social networks, for example, where people with few connections can be highly influential because they're in touch with one very important person, right? And one algorithm that takes this into account is the so-called PageRank algorithm. That's the algorithm which Larry Page came up with when he was looking for a way to return the results of a Google search in such a way that the important results appear at the top of the list, right? So to determine the importance of a web page, what he was looking at was the number of URLs pointing to a page, and would recursively compute a score depending on how important the pages pointing to that page are, right? And as a result, pages with few connections but associated with a very important page would still appear high on the list, and that's what you would make use of in these kinds of PageRank calculations on a social network, right? So that's the PageRank algorithm, which hopefully Jayant will be showing you in a moment. In general, if you want to perform graph analysis by means of graph algorithms, what we're offering to do so is two APIs, one in Java, one in Python, and the results of the algorithms are added to the graph as new properties, right? This can be measured, like in the case of PageRank, would be the PageRank value, which would be added to each vertex. In the case of a community detection algorithm, you would add a number to the vertex representing the number of the community, essentially. So you can group by community or whatever, or it can be complex things like a vector reflecting the embedding, as in the case of deep walk, right, where which is one of the graph machine learning algorithms which we offer, right? In any case, you can make use of these results from PGPL, and hopefully Jane will be able to demonstrate that in just a moment. Before we come to that, one more quick comment about the client software, right? On premises or in the user-managed cloud environment, we have a JShell client, or you can use the Python API, as I said, or we have a Zeppelin-based notebook, which you can use to execute the algorithms in Graph Studio. What we're offering is a notebook environment which comes with a Java interpreter. That Java interpreter has the full Java support, the full language support. Python is actually something which is coming up, but not quite there yet. And that Java interpreter not only allows you to do all the things you can do in Java, but there's also a few things which we've implemented which make it a little more convenient for you, in that we have a couple of objects already instantiated. Primarily what you'll see is the session object, which is being used, for example, to retrieve a handle on the graph, which you want to work with, or the analyst, the analyst, which is a helper object that allows you to execute the algorithms. At that point, the interesting question would be, Jayant, would you be ready to show PGQL and PageRank?
Okay. All right. So what we've done so far, we'd created a user that was graph enabled. We loaded the CSV files, and then I'd, out of sequence, but I'd showed how you look at those tables that you just created and create a graph from it. So we've created the graph, and now we are going to query and visualize it. So Hans talked about notebooks and the fact that notebooks support different types of paragraphs and environments. One of them is Markdown, which is just to document or annotate what the notebook is about. The second is PGQL, which is the graph queries. So PGQL, as Hans pointed out, is similar to SQL, where the difference is the match clause. And the match clause says, what are we looking for? What is the graph pattern? In this case, the graph pattern is we want source vertices, we want transfers, the destination account for that transfer. And we want to look for this pattern on the bank graph that we had created. And I want to limit it to just the first 100 results, because all I want to do here is get some idea about the graph. So I can execute that paragraph, and it'll just display it. We can view it in a tabular form, which is not very helpful here, but will be in a different query. And then you can look at the properties of those items. So if you right click on an account, for example, it gives you, well, that was the account ID, the label that I had changed and put as being accounts, for example. Now, the purpose of that, what we want to do here is we've got this bank graph. We're looking at it, and the real goal is to look for things that may be participating in a series of transfers that is a cycle, right? It starts at an account, goes through a series of intermediate accounts, and lands up back at that account. So we've got a whole bunch of them. How do we know where we want to start? So one way is, well, let's just look at those that have had a lot of transactions. That means either data transfers coming in or transfers being made from it. So this query simply says, I want to get the list of accounts. So give me the account IDs and give me the top 10. So sum the number of transfers in and the transfers out. Yeah, that's the number of transactions. I order the results by that number of transactions. Just give me the top 10. And that's the result. Here's where, all we want is a tabular result. We don't just want a list of, if I did this as a graph, it would just show vertices, and it wouldn't have the meaningful information, which is the number of transactions. So we find that 934, 387, either one of those. Let's see if that has a circular transfer. So now we'd use a slightly different construct. Hans pointed out that there's a lot of flexibility in this match clause. So I want to look for a path of up to length 5. So here is a way in which you specify that. I want to say that this is specifying a path. Along that path, every edge has this label called transfers, and the path is of length up to 5. And this is simply going to tell me whether such a path exists or not. That's all. If it does exist, it'll give a result. If it does not exist, it'll give null. So it says, yes, there is such a path. Now, if I want to find out what those paths are, I can do multiple things. One of the first things I can do is say, well, show me which is the penultimate account in that. So, path of up to length 4 deposited into some account, and then from that account into the original, so that I can see how many such paths there are. And here we get the result. So there's some up to length 4 followed by the final transaction back in here. Now, this is just one way of looking at it. The other thing that you can do is you can come back here, and if just view all the nodes at random, or look at it as in a different layout. These are all different possible layouts that we have. I just happen to think that the radial was appropriate in this case, which is why I picked that. The other thing is that, say we want to highlight and make the source vertex evident. I know that that account ID is 934. I can just say, make that bigger. Okay. So here what we've done is we've used PGQL. So we select everything that matches this pattern. The pattern says I start from account 934, up to 4 hops, goes to some intermediate account, lands back at account 934. I may want to actually show every step along the way. So I enumerate all those 5 hops. Start from 934, first transaction to the first intermediate, second, third, fourth, and so on and back. And here I chose the hierarchical layout because then I can see the actual set of transfers. I starts at 934. This is the first hop, second hop, third hop, fourth hop, and then back to 934 and the 5th hop. So that was showing the PGQL part and showing the queries and the power of that, the match clause, right? Now I said up to 4 or up to 5, but that's, in that pattern, I could say I want a minimum of 2, a maximum of 4. So, and then the intermediate account, and then, so this is between 3 and 5 hops. This is how you specify it. The other thing that you can do there is you can have this bind variable, if you're familiar with SQL, where you say, I want it, and I enter the account ID at runtime. So here I enter 534. What was the other one, which was?
Maybe you want 934 or 387.
387. So I could try 387 and execute that query. So that was the PGQL portion. And now we'll come to the portion for the algorithms. So now we would be using the Java API and therefore the Java interpreter. And you specify that by saying, I'm going to be using the Java APIs on the graphs. So the Java API essentially consists of a few things that are pre-built and then a set of objects that you use to interact with. The things that when you create a notebook and it instantiates for you is a session, and then the analyst where you run all the algorithms. So from the session, you get a handle to the graph that you are dealing with, in this case, bank graph. And then you can ask the analyst to run a particular algorithm on that graph. In this case, we want to run PageRank on that graph. So once you do that, you can then use, so what it did when it ran this, it tells you it added a vertex property. The property has the name PageRank, and it added it to the bank graph so that you can now use that property in queries in the PGQL queries. So here I'm rerunning the PGQL queries for account 934. I want between 1 and 6 hops. And the reason I'm running this is I want to show that you can then use the PageRank value. So this has a PageRank, and it is connected to other accounts that also have a relatively high PageRank. And you can use that in the highlights. So I can create a condition which says a PageRank above a certain value, increase the size, so that it becomes evident how this is connected to other accounts that are also high in PageRank, which simply means that those accounts are either themselves well connected to other connected accounts, so that is a different notion of importance. I had one notion of importance earlier, which I said, just show me all the accounts by their degree. So the number of transactions in and out. And the other notion, which was by PageRank. So let's compare the two. So look at the top 10 by PageRank. So we have 387, 408, 934 is also in that list. And this was 934, 387, 135, etc. But there's 380, which is here. There's 222 and 4, which are in PageRank, but not in this. So let's look at these two different notions of importance. Let's look at 222 and see why did it show up in top 10 in PageRank, but not in the number of transactions. So let's look at its two neighbors, who is it connected to? And again, I've done a highlight which takes PageRank into account and makes those larger to show that 222 is connected to another important account, and therefore its rank has also gone up. And then let's compare 4 and 380. 380 showed up here in the number of transactions, 36, either deposits or transfers out, but did not show up in this list. 4 showed up here, but not in this list. Let's see what's the difference between the two. So do the same thing. Look at the two neighbors of those. And this is account 4, which showed up in the PageRank. It's connected to this one, which has a high PageRank. This which has a high PageRank. This which has a high PageRank. This which, so it's connected to a number of these that have a high PageRank. 380, on the other hand, is connected to things. Let's make it more evident. 380 is connected to things that do not have a high PageRank, and therefore itself, it did not have a high PageRank. So Hans, that was a bit about how you use an algorithm. So how do you use the Java API? And then how do you use the results of that algorithm in queries and in visualizing those queries and interacting with the graph? So back to you.
Yep, great. Thanks a lot, Jayant. That was very helpful algorithms. Just to briefly recap, what we did in this little walkthrough today was I explained how you would create a graph from relational tables, ending with a PGQL statement, right? Jayant showed how that works in practice. Then we talked about how to move data into the appropriate data structures. We've gone over the fundamentals of PGQL. Jayant performed a number of graph pattern matching queries just a moment ago, in this interactive way, visualizing them in different ways. And then we've really only just scratched the surface. And finally, we've briefly touched on the topic of graph algorithms, at least showing you one algorithm and how to use it, in this case, PageRank. You saw Graph Studio as a part in Autonomous Database. As I said, you could potentially also use the Graph Server and Client Kit But in that environment, you wouldn't have all the automation which we provide with Graph Studio, and you wouldn't have the UI to model data as a graph, right? So I hope we've given you a bit of an idea of what graph databases can do, how powerful they are for the purpose of analytics, essentially complementing what you can do with relational databases. They're particularly suitable for those cases where you are looking at connectedness, the topology of the graph, providing insight into relationships, into dependencies, into behavioral patterns, and the like. They can be used very nicely as additional features for your machine learning, and in fact, it's also what is becoming pretty popular in the industry. And really, to make it simple for you to get started, what we're offering is Graph Studio, with the modeling capabilities. You can manage the graph data, you can query the graph. You have the notebook UI with all the interactive visualization and analysis, and all of that sits on top of the in-memory analytics engine, which has all these graph algorithms pre-built into the environment, plus PGQL for pattern matching. Sitting on top of the autonomous database, meaning it's using the autonomous database with all its secure and scalable graph storage, and inherits all the self-driving, securing, self-repairing capabilities of the autonomous database. I hope you found this little session useful. The landing page where you can find more details on our graph offering is oracle.com/database/graph, or if you want to take the shortcut, you should say oracle.com/go-to/graph. We have been talking about the live labs. You have the dedicated link to the workshop, which Jayant used as the basis for the walkthrough. If you're looking for live labs in general, we have the bit.ly/go live labs, which offers you tons of live labs workshops. But for graphs in particular, if you search for graph, you find a number of sessions or a number of workshops on graph technologies. If you want more explanations in the form of video recordings, we have a series of Ask Tom sessions, which are also included on the page here. Plus, you can find the recordings of previous sessions, including the one on relationships unlocked, which was sort of looking at the use cases on our YouTube channel, youtube.com/c/Oracle Spatial Graph. If you have any questions, feel free to reach out to myself or to Jayant. You can follow us on Twitter. If you found this session useful, you're very welcome to tweet about it. You can also join the LinkedIn Oracle Spatial and Graph group, which is not actually an Oracle owned group, but it is managed and maintained by us together with the user group. And finally, what we'd be really interested in is your feedback on today's session. So if you would please just spare 15 seconds of your valuable time by going to bit.ly/feedback-210615 and let us know how you felt about today's session. That brings us almost to the Q&A. While I'm sort of mentally preparing for the Q&A, maybe Tara, you can take over and briefly talk about the developer masterclass, will you?
Yes, thank you, Hans, and thank you, Jayant, for this awesome presentation. So before we get into our Q&A, as I mentioned a little bit before, There will be a quiz on today's workshop, and after completing the quiz and to recognize your commitment and earned expertise, you'll earn a developer masterclass badge that you can share to your social media. So each session in the App Dev Masterclass series will have its own badge, and it will lead up to the eventual title of Developer Pioneer. So I will go ahead and drop the link to the quiz in the chat now. And I did want to remind everyone as well that the recording will be sent out to you guys via email within the next couple of days. So if you joined a little late, you can follow along in the recording when you try the lab on your own in your free tier environment. So, and we also have a few additional links. So we have some other series going on, cloud coaching, and then our developer live. So feel free to check these out as well.
Other thing is, if we have time, I think there was a question the last time around about schemaless and being able to add elements to the graph on the fly, add a property, add a vertex. I can certainly try demonstrating that if we have time. Obviously, it's unscripted, so just like the other stuff crashed, this might crash, but I can give it a try.
That's what makes it fun. So let's give that a go.
I'm going to use something called SQL CL, which is a command line interface, to the SQL that you can do from database actions, SQL.web, right? And I'm going to connect as myself to my database instance. What this is doing is first telling SQL, where is this database wallet? And second is logging in without showing you my password. Anyway, so once I've logged in, I'm connected to my database instance, and we've got the bank graph, for example, and a bunch of others. What I want to do here first, I don't want to clubber the graph that I had for the demo. I want to create a clone of it. So I'm going to call an API that makes a clone. And okay, I'll look that up in just a second as to what the correct thing is. So Roberta, if you have it off the top of your head, you can tell me and I can enter the correct command. Or one of the things that is there is...
So you'll probably want to do a describe, not a decribe.
Yes. I think it's called clone PG, but all right, so you got all the various flavors of analyze, collaborative filtering. All right, clear. Hopefully the next one is clone graph. Okay, so it was clone graph, not clone property graph. So Hans, remind me to go off on my usual rant about API design on our next design goal.
Will do.
All right. You know what? I'll probably just start from scratch on this. This thing is going to take a while. So. So I'm going to clone that graph, and once this runs, what it's going to do is will have created another graph called clone with the relevant tables. So we want to, let's say we want to insert information about account holders, right? So that I will be using something known as PGQL, right? I can execute PGQL from this interface. So I'm going to say that's what I want to do. I want to start executing PGQL. And the PGQL statement that I want to execute is an insert where I'm going to add vertices of type persons that have certain properties. I'm just illustrating here, so I'm going to give the first name as being their account ID, their ID being the same as an account ID, 1-to-1, one person owns one account. Their first name and their last name are simply the account ID followed by the string first name, last name. If this works,
I hope it's clear to everybody that we are using SQL.cl here, right? We have this wonderful little plugin that allows you to do PGQL in SQL.cl, right? So your probably favorite command line tool can speak PGQL as well. Here we are.
Right. So it inserted a vertex of type persons, 1,000 of them. The reason it says 3,000 rows modified is because one row has the person with their ID, the second row has their person with the first name property, and the third row has the person with the last name property. So we did that. Let's add an edge to the transactions that, let's add an edge all righty, I can do this, it's fine. I should have done that commit before. I may have to exit and enter to get a new session, but we'll see. So this is going to just take, the 5,001 transactions that are there and add a new edge. And the edge property is called transaction date. If it works, it should update 5,000 rows. Okay. Now that we've done that, I don't think we'll do. Okay. Let's add edges between the newly created, the persons and the accounts. So I'm going to insert an edge that is between the account holder, the account. The label for that edge should be has account, that is, this person has this account. And I'm simply going to say that the ID of that person should match the ID of the account. Just a simple way of inserting an edge. And hopefully this won't give me that parallel update issue. If it does, I have to log out and come back in, but there we go. Okay, so we have here a newly created graph with newly added edges and vertices. So this bank graph clone. If my instance is still up and running, I should see the clone here, which I do. And I created, it tells me you created this directly using SQL/PGQL. So I come back to my notebook.
Magic.
And I went to the graphs. Well, let's see. I went to the graphs page, and I can see that there is this clone that I had just created that exists. And it tells me that I created this using PGQL. And I want to load it into memory. Actually, let me do it from here so that I can analyze it and look at it in the notebook. So I'll load that into memory. Once that is done, I should be able to come to my notebook. And I should be able to query it, which is, I added persons, right, who have an account, and accounts have transfers. So if it has indeed been loaded, this query should execute, and I should get a graph, which is people and the transfers. And if it doesn't work, it means I need to just first, I should have checked whether or not, I should have waited for the graph to actually be loaded. So let me see if that happened. It did. Let me confirm that it does indeed show up.
That's the nice thing of doing things live. Keeps the presentation interesting and exciting because you never know what happens next.
No, that's fine. I may have also outsmarted myself, which is what I think I did over here. I forgot to turn on the results. Right, there you go. So let me just execute it once again so that it actually executes. But yeah, I had turned off the results so that it wouldn't confuse me on the previous session, but it confused me on this one. So here we go. We've got, let's zoom in a bit. We've got people, accounts, transactions between those accounts. So that was to show how you can add elements to a graph. And back to you, Hans.
Yep, I think that pretty much wraps it up. Thanks a lot again. Tara, any final words from your side?
No, thank you. Thank you, Hans. Thank you, Jayon. And thank you everyone again for spending your time here with us. I will go ahead and end the session now. Thanks. Have a great day, and we hope to see you all next time.
Thank you, everybody.